have, so Margaret, you have control on muting, right? Is that right?
Wingsy does. So, yeah.
Wingsy does. Everyone's muted, okay? All right. So it's a great pleasure that we introduce we're starting our VIP seminar series, kicking it off again. This is our first in the COVID period, and Andrew's our guinea pig. It's got a bit of echo. So anyway, it's a great pleasure. I might tell you what I might do.
Hey, Graham.
Yeah.
There's a lot of feedback.
I know, and I don't know what it is, but I've just turned my mic on and off to see if that cuts the feedback out, which it seems.
That's better. That's good.
Seems to have done. I'll just go quickly. So we introduced Andrew. I've known Andrew for a number of years. He was a graduate student at the University of Washington. I guess you were Jim Holton. You're a protege of Jim Holton, I believe. Is that right, Andrew? Was that
correct?
Yep. Anyway, Andrew's been at NCAR for some time, and he's probably one of the premier global modelers now. We could consider him one of the premier global modelers of the Earth system. And he's just recently come back from a sabbatical at Oxford University. And I would presume that the topic of your seminar today, Andrew, is from research you did while you were in Oxford. Has to be, right? Because this all happened when you were in Oxford. So by inference, I think has a bit of an Oxford flavour to it. So it's with that introduction, it's a great pleasure to have Andrew as our first of our virtual VIP seminars, and we really look forward to it. Thanks.
Great. Thanks, Graham. Thanks for coming. Thanks for attending, and thanks for inviting me. I sort of was invited as a regular speaker and encouraged the virtual visit. It's been great to talk to some people yesterday, and I'm looking forward to talking to more of you later this afternoon. I thought I'd deviate a little bit from the ordinary here, and actually, as a lot of us scientists got sent home in March, and in England it was no exception. It was sort of we were basically told one day that, oh yeah, by, in 36 hours, you won't be in the office anymore. So when you come in tomorrow, take whatever you'll need. And then everybody ended up at home, and you leave a bunch of scientists at home with a bunch of unfettered access to the internet, and interesting things start happening. And so, like many people, I've sort of thought about what this pandemic means for our science and what are the science implications of the work that we do, and I'll describe a little bit of that. And that's sort of the theme, these intersections between this COVID-19 pandemic and climate change. And so again, as Graham said, thanks to the University of Oxford for hosting me last year, as well as NCAR and NSF, our major sponsor. So the interesting thing that I'll sort of weave through this is that both the pandemic and climate change are two global interconnected crises with evolving science. The speed of the pandemic is not something that most of us climate scientists are used to. But other than that, they're very complex problems. They require both global, national, and local changes in behavior. And there's a lot of interesting analogies, and then places where our science intersects. So I'm going to talk about a couple of different things, and this is sort of along the theme of what does a cloud and climate physicist know about pandemics? And I'll assert that in this case, we actually know quite a bit about pandemics. I'm going to talk a little bit about the physics of clouds pollution and how that relates to virus spread. If you think about it, basically a cloud is essentially drops of salt water and organics, and it's not dissimilar from clouds of drops that people expel out of their mouth that may have salt water and organics in them, some of those organics being viruses. And then there's an interesting angle of how the environment and air pollution can affect both airborne drops in your lungs and some of the comments that people are making about susceptibility to the virus and other things like that. Second is looking at how air pollution and emissions changes occurred during lockdowns, and what the impacts were on air pollution and also then the longer term of what this might be for climate change, and that's specifically looking at things like the radiative effects of emission changes through things like aerosols and changes in, for example, contrails in aviation. And I'll show some examples, actually some model simulations of differences shown here due to assumed changes during COVID from baseline conditions. And then the interesting thing to me also, as somebody who models climate and thinks a lot about uncertainty, is noting that there's large uncertainty in modeling pandemics. The forecasts that we've seen have been frequently wrong. And needless to say, those of us who model weather and climate know something about bad forecasts and incorrect forecasts. We also know how to characterize uncertainty. And what we know about weather and climate prediction, and actually I think can help us at least categorize the uncertainty in epidemiological modeling. And I'll relate, you see the chart over here of what's essentially scenario uncertainty in climate modeling from the IPCC with different historical emissions trends to different control measures that might be scenario uncertainty in epidemiological modeling. So that's sort of the overview. Let's talk about clouds. Let's talk about clouds that come out of people's mouths. Human phlegm or sputum, which is essentially the scientific term for stuff that comes out of your mouth and nose, is essentially salt water and organic molecules. It's not really that different than sea spray. And the dynamics of it are like small cloud drops and aerosols. And of course, in the case of pandemics, it's the aerosols that we're really interested in, and it's the impurities in those aerosols. So viruses exit the body in water drops. Viruses are tiny. They're 0.1 microns, 1/400th the width of a human hair. It's not the size of the virus that matters. It's the size of the drops containing the virus that matters. Viruses don't come out of your mouth in clean air. They come out of your mouth in water drops. There's two groups of drops. There are these, what's interesting is there's these larger spray drops or droplets that are sort of on the order of 150 microns. The drops occur with the larger ones with more forceful, say, talking or coughing. And then there are these aerosols. So these things are on the order of 2 microns typically, but they have a size distribution, of course. And the volume of these things comes out with breathing, talking, and coughing. Large drops, or these large spray drops, tend to hit the ground quickly. What's interesting is that the large spray can go several meters. The small drops, because of their sort of volume to drag ratio, it's hard to get them to go more than 2 meters quickly. And you can think about this as try to throw a feather. And regardless of how far you throw a feather, it's hard to get it very far in front of your face. If you put it or in front of you, if you accelerate the feather rapidly, it has more drag and it doesn't go very fast. However, the feather, unlike say a baseball that you can throw a long distance, the feather is going to stay in the air a lot longer. And that's one of the issues, is that a lot of this 2-meter distancing is predicated on how far you can cough or sneeze on somebody. And those drops will go about 2 meters, or how long this cloud of small drops stays in front of you. But the problem is that it stays in the air for a long time, at least in a closed environment. The concentrations fall off rapidly in open air, and they disperse very, very rapidly. So these are some of the physics that we understand that help inform what's happening in the environment. And of course, this is all very relevant for pandemics. And what's interesting is that there's not that much research on this. And those of us around who have access to laboratories or who work on instrumentation, we have a lot of instruments that are actually made for airplanes that can sample these sorts of groups of particles, but we don't really apply them in these ways. And then the people that work on viruses don't really have access to a lot of these sensitive aerosol instruments. So there's still, I think, there's actually a gulf in the research community. So then the second question is, does this virus actually survive in these water drops, and for how long? These aerosols can persist outside of the body for on the order of hours before depositing on surfaces. Some of them deposit very quickly on surfaces. Viruses survive for on the order of an hour or two in aerosol. The interesting thing is that the viability, and here's some examples of looking at viability studies and that's sort of a log scale for both SARS and then COVID-19 on the top. And so SARS is a coronavirus in the 2003, essentially, coronavirus with different properties for how it was distributed, and it wasn't as big a pandemic, but it was still an epidemic or pandemic in 2003. So the half-life of a virus is about an hour, and what's interesting is that the way that you measure viability is you basically let aerosol circulate, and you have to actually physically collect it and then culture it. And if it cultures, then it's viable. If it doesn't culture, it's not viable. It's a rather crude measure of measuring viability because you can only do it on discrete samples. Now, these studies don't really test temperature or humidity, which I'll get to in a minute. What's interesting is that the severity of illnesses with COVID seems to be dependent on virus contact extent or the dosage. It seems like you're unlikely to get a severe case from one virus particle or a small concentration of virus particles. And you'll notice that most of this work has appeared actually really, really recently in the literature. This social distancing comes, as I said, from some of the issues with, saying that you should stay 6 feet apart, comes from your ability to sort of cough on somebody or this initial cloud of drops. But it's also done on empirical studies of infection in high-risk environments. And so there's been a couple of different, whoops, where'd that go? This is looking at a study that looked at where masks were worn and where they weren't worn, and sort of distribution of infection risks for mostly the flu. There were some studies in here where they did look at SARS, for example, and one or two that were able to look at COVID in early 2020. But what it basically shows is that if you, with these baseline risks, if you stay farther and farther apart, you can cut the baseline, you can cut the absolute risk pretty significantly. And the relative risk is actually, the baseline risk goes down in absolute terms, but the relative risk goes down even more dramatically. You can see there's a fall off of factors of 2 or 3 in the relative risk with difference. And so that does depend on the baseline for infection, but it also in these other studies argues that trying to stop the drops and wearing masks actually strongly favors risk reduction for infection spread. One interesting other aspect of this, where some people have done some work in the field, is looking at temperature and humidity and how they affect virus spread. And this gets to the fundamental question of why does flu peak in winter? There's many things that affect flu transmission and the susceptibility. One of the more interesting things I read about was that the way they look at the susceptibility to flu is what they call it's a guinea pig experiment, where they take 2 guinea pigs and they expose an infected guinea pig to another guinea pig at different temperature and humidities, and they see how well the flu transmits. And they do this in isolated cases. And what they find is that lower humidity and lower temperature gives you more flu transmission. And what we get in the winter is, if you look at these climatologies, we see lower temperature and lower humidity. And that occurs pretty much both indoors and outdoors. But what's also interesting is it doesn't go away. I mean, people said at the beginning of the summer, oh, well, flu goes away in the summer, so COVID will go away in the summer. It was pretty obvious that you were seeing infections in warmer climates. I mean, when places like Singapore are fighting infections even in February, temperature isn't really going to kill it. What's interesting is the susceptibility may also be different, and this is one of the reasons why they think flu, in addition to this transmission being more at lower temperature and lower humidity, you can get different outcomes with the same transmission. So people's lungs are more prone to infection with dry air, and immune systems are weaker, both for everything from having to work harder in colder temperatures to less vitamin D. I think there's a variety of medical reasons why that's the case. And then the other issue, of course, is people are around each other more if they're indoors in wintertime when it's cold. So there is the question about COVID and what's going to happen with flu season, and everybody's worried about that as we go into the northern hemisphere. But this is actually interesting data from the southern hemisphere. So Of course, in preparing this talk, I went beyond a lot of our usual sources. So this comes from the World Health Organization FluNet site, and it's showing on the top the flu season in Oceania, so Australia, New Zealand, and the Pacific Islands for 2018 and 2019. And we're in week 37 of the year. So this is basically starting in about August. It goes till December and then starts again in January. And you can see flu season peaks in about week 20. It goes basically, that's something like April or May. It starts in May and then it goes through August. And right about now, it falls off in August in the Southern Hemisphere. Well, continuing this time series, this is 2020. And you can say, well, what happened to the data? Well, the answer is you can see over here with the documented flu cases, not just in Oceania, but this is now Argentina and Chile and South Africa as well. There was no flu season in the Southern Hemisphere this year. And that is interesting. The things that we're doing to keep ourselves safe and socially distant, reduce human interaction, reduce the spread of drops in air between people, and that applies to flu as well as it applies to coronavirus. That's not to say don't get your flu shot, but it's just to say that it may not be as bad as everybody's fearing this year if we continue to try to control for the coronavirus. We also will probably control and mitigate some of the flu season. So what have we learned about, or what has a cloud scientist learned about viruses? Well, drops remain in enclosed spaces for some time. I'd still like to know, and we haven't figured this out, whether the infection happens in the big or the small drops. I think we're learning that it's probably the small drops, not the big drops, based on patterns of infection. Viruses can last an hour or more in enclosed spaces. There's too much dispersion outside to matter. For most people's behavior, it seems like restricting indoor activities, making sure you're wearing a mask with indoor activities, that actually does seem to be working epidemiologically. Social distancing is based on physics. You can't move small drops rapidly more than 2 meters, and you can't move big drops at all more than 2 to 4 meters. But again, it's the rapid dissemination may not be relevant in closed environments. Masks do reduce transmission. This is critical for high-risk environments. It's probably even good for low-risk indoor environments. Simple masks stop most big drops and many of the smaller ones. By many, that's on the order of 60 to 80%. And so if you can knock that down, that actually, I think, does a lot of good. And this seems to be the case both from available data from people playing with masks as well as from the epidemiological data. And of course, what we know is that I'm not wearing a mask so much to protect myself. It's mostly, or it also is that a mask protects you from me. It's sort of common courtesy. And the big issue, of course, that we know with this coronavirus is you don't know if you have it. So at all times, you have to basically assume that you could be spreading it to people. It's amazing how it is totally socially inappropriate even to cough or sneeze in public in the presence of other people right now. That's pretty interesting. So now moving on towards what we traditionally think at the large scale, and I guess the bias is I've done a lot of cloud microphysics, so in thinking about that, I dove into a lot of the microphysics of drops in the last couple months. That was mostly a literature review. Now I'm getting to things that actually we've been sort of working on. At the larger scale, pollution may actually impact the physics of virus transmission. There's evidence from Italy where they found RNA from the coronavirus attached to air pollution molecules. Specifically, I think it was brown carbon. Pollution is less dense than water. It might allow farther travel. It's very speculative. They found pieces of the virus. It's not clear whether they didn't test for viability. The other interesting avenue where there have been a few more studies, but again, this is sort of correlation, not causality, is that air pollution causes lung disease. It causes chronic lung problems, and we know it results in premature death around the world. That's partially because pollution increases the receptors in the lungs, actually, the corona protein that it adheres to. It causes reactions in the lungs that do that. So there is a theory that people with more chronic lung problems caused by living in polluted regions may be more susceptible to severe coronavirus infection. Of course, there are other correlates with this, particularly those regions may also be regions of poverty. They also may be regions where people can't socially distance, so there may be other covariates. Some statistical analysis, particularly in the United States, shows moderate impacts even when trying to control for those covariates. So I think the jury is out over whether that theory actually holds in a statistical sense. But there were some recent reviews trying to look at this issue in some of the public health journals that I was looking at. And I still think we don't know, but there is some evidence, particularly in this second avenue where regions with higher incidence of lung damage due to chronic pollution may actually also have people that are more susceptible to coronavirus infections or severe infections. And of course, the pandemic had big impacts on pollution. So pollution's associated with transport and industry, and when there were lockdowns in the spring, and even now, transport for people has dropped in many cases because people are moving around very differently. And even industry halted during the height of some of the lockdowns, and there were big shifts in usage patterns for things like fossil fuels. So of course, here's aerosols over India from 2019 and 2020, and this is the difference. This is from NASA's Earth Observatory, but a caution that doesn't really control for meteorology. And there's been a number of studies that have actually shown this, that you can get this effect if you pick any random set of years. I mean, it's consistent with the lockdown, but it could just be because 2020 had more rain than 2019, for example, in March. The clearest signal is actually in transport emissions, which you can't fully attribute to meteorology. So these were pretty neat pictures of satellite nitrogen dioxide. So these are emissions from internal combustion engines over Europe, cars, trucks, and ships. And you can clearly see there's big reductions over the same period in 2020. So if you look at Madrid, that region's down about 50%. But what's more astounding also is you can see this is a nice map because it shows the road network. So these are the autopistes in France, and you can see even the networks in the Autobahn in Germany. And you can see the higher NO2 emissions along the highways that actually disappear in 2020. And then this has all kinds of knock-on effects, of course. But and I know I talked with a couple other people doing work on this. You can also see these shipping emissions here. But of course, what's interesting is if you look at the shipping emissions here in the Atlantic, there looks like there's more shipping emissions in 2020 than there was in 2019. And in Northern Europe, that actually has to do a little bit with the meteorology and the difference in meteorology that actually occurred. So air pollution is complicated. This was a year's worth of pollution measurements in London. I was looking at sometime in April and May. And what's very interesting is you can see, if you looked at the NO2 again, which is transport related, when the lockdown started in February 2020, the NO2 dropped pretty dramatically. But you'll notice the ozone picked up, and there's almost evidence of an anti-correlation of NO2 and ozone, right? Well, what's going on? And you can even see this a little bit in some of these other periods before the lockdown when these things are actually anti-correlated in the year before. Well, ozone is the result of air chemistry, but it's also other organic compounds such as VOCs. And with lots of VOCs, you can actually increase ozone if you decrease NOx. It has to do whether it's VOC limited or NOx limited. And then the other issue is that ozone actually also increases with sunlight. And so as the sun comes up, you see there's an increase from March to April in 2019, and there's an increase from March to April in 2020. So you have to actually be very careful when you look at air pollution effects from short records like this during the pandemic. And again, these reductions can be temporary. So this is nitrogen dioxide levels in China, which if you look at the Lunar New Year and you correlate by that, then there was lockdowns which began, or there's a drawdown that happens right before the Lunar New Year, before everybody goes on vacation. And then normally it rebounds about 10 days after Lunar New Year. Of course, this year that didn't happen. It took about 40 or 50 days, but by 60, 70 days after Lunar New Year, which is at the end of January, so we're talking about April or so when they started to get industry going again in China, things were pretty much back to normal with the NO2 levels in China. Some things don't recover, however. So this is data on aviation, and what you can see is this is the total daily number of flights color-coded by year. So it's a series of annual cycles, and you can see an increase from 2016 to 2019. It's a secular increase as aviation increases at a few percent per year. There's a couple of notable things on here. There's a annual cycle where there's slightly more flights in Northern Hemisphere summer because of summer travel in the Northern Hemisphere. There is a very strong weekly cycle. That's all those peaks. There are 52 peaks in there. That's because there are fewer flights on the weekends. It's still dominated a little bit by business travel. And then you can also see this spike right here. That's Christmas, right? That's when nobody flies on Christmas, so there are fewer flights. And that's a dip you see every year. Well, this is 2020. Things were moving along with an expected increase in January, and then in February that started to fall off, and then the lockdowns happened. And I put on sort of, this doesn't go to zero, so this is what 100% approximate would have looked like on average for 2020, and this is 50% of what that hypothetical value is. And you can see aviation emissions fell off to something like 70%. They fell off to about 30% of what they were, and they've recovered to about 65% of where they were. This is based on total number of flights, and the data is actually updated through this week. This is Flight Radar 24. They're releasing the last 6 months on their website, and they kindly provided me with data for the previous 4 or 5 years to be able to actually build statistics for this. We're actually using this data to assess the effects of contrails that I'll show an example of in a minute. So getting to this level, we actually then can look at some of these emissions changes, and we can actually hypothesize what these changes are, and we can put these emissions into an Earth system model. So what I'm using is the community atmosphere model, or the community Earth. It's inside of the community Earth system model, so it's NCAR's latest Earth system model. And we're doing these simulations where we use an atmosphere model only. We fix the surface fluxes, and we fix the SSTs, sea surface temperatures at observed, and then we nudge the winds, and we can optionally or not nudge the temperatures. And what this means is that we can control for meteorology. We spin the model up in 2019, and we restart it in January 2020, and we're running, it's not 4 months anymore, we're running it for 6 months, soon to be 7 months, till the end of June 2020. And of course, running a climate model for 6 months is cheap. They've been designed to run for hundreds of years. So that means you can actually do multiple ensembles. And so we're actually doing 20 ensemble members with slight perturbations. We're using a series of emissions perturbations that were generated by Piers Forster. Piers did a nice study where, based on some work from Corinne Lecaire, who compiled data sets and inventories of primary sources in developed countries. What Piers realized and his collaborators is that they could correlate that with Google mobility data from cell phones, and then actually use that to extend those emissions reductions to more like 150 different countries. So pretty much global disaggregated emissions by sector. So these were applied to help scale some of the baseline set of emissions from the CMIP6 archive and CMIP6, the coupled model and comparison project, which many of the Earth system models like CESM used their emissions data sets for the latest IPCC report. And what this basically does is it prescribes during a data set, and this was done for a longer period of time, but we're looking at basically just this period in 2020 where you have a sudden lockdown and then a recovery, and then using these 2-year blip scenarios that recover. And we're only running the first 6 months, so it only gets to about here, but they recover after about a year and a half to meet the emissions again, or there's some green recovery scenarios and one that has a fossil fuel rebound scenario. So we're using the assumed emissions that have been validated against, for at least the reference period of the last 4 or 5 months that have been validated with sort of the mobility data and the inventories. And we run the model 20 times, and we can either use daily or monthly data sets. And we basically then can look, we're also doing aviation simulations with weakly scaled flight emissions and a contrail parameterization in separate simulations. And I'll show one slide on that in a minute. So what you basically see is we see effects here where we actually, this is a zonal mean, and the 1 sigma uncertainty across the ensemble members is shown by these shaded regions. So you can see where things are significantly different than a zero perturbation line. And that's based on, again, 20 control ensemble simulations with essentially continuing the baseline emissions and not the scaled emissions. Can I move that? Yep. Okay, so you can see this is the visible aerosol optical depth, and you can see a fall off in the northern hemisphere in the subtropics to mid-latitudes. That's mostly driven by both changes in sulfate and changes in black carbon. This is total integrated black carbon. And you can see actually that a daily correlation with the daily emissions actually give you less of an impact than the monthly, smooth monthly emissions. I'm not sure why that is. It may be a correlation with meteorology. We have to actually look at that to see how significant it is. And there are some changes that are significant then because of these peaks in the clear sky top of the atmosphere flux. So you've got reductions in aerosols. Whoops. Where am I going? Back. Reductions in aerosols that lead to decreases in the aerosol scattering. So that's actually an increase or a warming in the radiation in the system. And then you can look at the cloud radiative effects. There's some, again, this is actually interesting because this is sort of a direct radiative effect of the aerosols. And this effect here is actually an indirect effect of the cloud. So we see few changes in the southern hemisphere, but we do see cloud changes in the cloud microphysics. This is a slight warming, which is barely on the edge of significance. And that increase in warming is a result of a decrease in liquid water path, a decrease in cloud drop number with the drop off in aerosols, and an increase in the cloud drop size. These are actually not significantly different than zero, but they add up to radiative perturbations that are detectable. And the global average of those radiative perturbations and regional averages is detectable. There's a lot more noise in the tropics. That's because the tropics and subtropics have convective clouds. Those convective clouds are not as well controlled by the nudge meteorology, and so they vary a lot more with the different simulations. And these radiative flux changes, as I'll show you, are actually significant. So if you take the monthly global mean, and this is going from January to June right now, and this is sort of a control versus the COVID, you can see differences here. So fall off in aerosols over time, fall off in sulfate over time. That actually leads to a slight decrease in the liquid water path, which then recovers. And that, if you add up the direct and indirect effect, you get a difference in the long wave and short wave at the top of the atmosphere, something like 1/4 of a watt per meter squared. That's maybe 10 years of emissions. It's maybe 10 to 20% of the total human anthropogenic forcing of climate right now. It's probably closer to actually 10%. So what this says is, did we actually affect climate change? Well, we did for a few months. Recovery's probably already started. Many of these sectors are actually recovering, although we're not going to see a full recovery for a while. And again, this is hypothesized based on a particular emissions scenario. There's changes both in the clear sky and the all sky. The clear sky is mostly direct effects, and the all sky is mostly indirect effects of the aerosols on clouds. So you can actually go through and figure out what would that actually do to global warming, but broadly, it's a small perturbation on it. Just for fun, we looked at what were the changes in surface temperature and when we don't nudge the temperature. And if you look in April, when April was actually the sunniest month in the history of the United Kingdom, going back about 250 years, there was a place outside of Oxford that recorded no precipitation in the month of April. And that's like never happened before in the United Kingdom, which is obviously, that was one of the challenges of somebody from Boulder and going to the UK for a year was dealing with that climate. But April was nice. And actually, the interesting thing about April was even controlling for meteorology, this reduction in aerosols and slight increase in radiative flux at the surface, model simulations do actually show slight increases both in the minimum and maximum temperature during the month of April in these different ensemble members. And you can see if you look at the global map of that, the changes in black carbon over India also indicated that over India and China also would imply changes in the minimum surface temperature and maximum surface temperature over these periods. So just something interesting to look at. It's a small perturbation, and I don't think in a purely statistical sense these numbers are significant. So is any of this real? Are any of these effects that we see real? Well, we can compare to observations. The interesting thing is the change is smaller than the variance due to meteorology, and we cannot rule this out based on observation. So there's some nice work that Michael Diamond and Rob Wood did looking at data from February 2020 from the MODIS satellite, and they looked both at AOD and effective radius, and they looked over China. What they did is they got an observed value, and they created an expected value based on previous years and the climatology, and sorting out, and then trying to control for the meteorology. And they got differences there. And you can look at these differences in both AOD and effective radius. And these are the simulated differences from the simulations I was showing you in AOD and effective radius. And you'll note that the scale here is much smaller than the scales here. This is on the order of a small fraction of this. And what it basically says is the perturbations that we would see in an isolated, controlled sense when we look for the changes in these models are much smaller than these sort of random, what looks like a random variation we see in the observations. So it's highly unlikely that we would see these effects in observations. We can't certainly rule out the scale of the changes I'm showing you based on observations, because they're much smaller than the perturbations seen in the observations. One last comment on contrails. So we've also run with this big drop in aviation emissions. And if you look at June, when we're back to on the order of 50 to 60% back up in aviation emissions, we still see that this is all aviation. We're still doing simulations right now for COVID, but essentially the loss of contrails heat, and in certain regions you can see something like an extra watt or watt and a half from a 50% drop in aviation emissions. It's about 1 watt per meter squared regionally, but the global impact, because it's so isolated by region to the regions of high traffic density, is pretty small. It's only on the order of a 20th of that, really. So because of the aerial extent of this. So we are exploring the effects on surface temperature of this, as well as the radiative fluxes. And it doesn't look like there's many significant effects on surface temperature. These are perturbations that happen high in the atmosphere, and most of the effects seem to be on the upper air situation. So now I want to talk a little bit about climate modeling. Of course, I think most of you know what climate is. Climate is what you expect. Weather is what you get. Climate is the distribution of weather states and its probability. And chaos theory was actually developed by a climatologist, by Ed Lorenz, in a very nice paper in 1961, to explain the Lorenz models designed to explain why the weather is not predictable after 10 days. And it does that with the use of a simple attractor, but it shows how the chaotic behavior and what that looks like. Of course, you can have climate change where you take this distribution and you shift it to more hot weather. That's typically how we view it. You can also actually have climate change where you just change the variability. So you actually get more hot and more cold weather. That can also result in climate change, even if the mean doesn't change. But we typically think about climate change shifting the distribution. So let's talk about what COVID would do for climate change. This is the change in global energy demand by fuel. And this was a review that the International Energy Agency published at the end of April, accounting for the lockdowns, which were in the process of recovering. And you can see the pretty dramatic drop in fossil fuel use in 2020, pretty much unprecedented. This is in relative terms, it's in absolute terms as a delta. It's not in relative terms. But what is interesting is that coal, gas, and oil fell off. Nuclear power was down a little bit. Renewables actually held up. It didn't make sense to shut them off or do anything with them because they were free. And this shows a loss in demand, particularly for oil, and that's transport related, of course, because people started traveling less, and the distribution of transport emissions changed pretty dramatically. From this same review, this puts it in a little perspective, so you can take these fossil fuel numbers and you can turn them obviously into CO2 emissions, and then you see where you get to, and you can see those annual change. That's a pretty dramatic drop. If you look at the bottom, it's the largest one-year drop in gigaton terms in carbon emissions ever. But if you look at the time series, it's really only about a 10%. It's actually less than a 10% drop in total CO2 emissions. And that's taking the drop and estimating it over the whole year. So if you extrapolate that drop, they're expecting an 8% fall in CO2 emissions over the whole year from this. So not a huge blip in our carbon emissions, even though most of our lives have been upended in various interesting ways. And if you think through it, that's not entirely unsurprising. We're still using energy right now in me talking to you and you listening to me in heating and cooling and internet and lights and all that stuff. So a few lessons is we stopped most air travel, most commuting, and we stopped 75% of car use. And even that was only 20% cut in fossil fuel emissions. As we recover, it's only going to be about less than 10% for the year. So that doesn't solve climate change. And it also, this is offset by a warming due to reduced pollution. So these reduced aerosol cloud effects that I quantified on the order of 1/4 watt per meter squared happened at the same time that you do this. So obviously, if this has an interesting policy implication, you can't just stop the economy to solve climate change. You have to actually evolve it. And it also means that non-essential travel, even commuting and aircraft, are not necessarily the main issue. Fixed sources, power plants are a major source of our carbon emissions. All the fossil fuel systems that supply all the things we need, we may not be driving around as much, but the trucks are still driving around. They may be driving around more because they're delivering stuff to your house. So the good news is renewables have held up, and that's the largest reduction in dirty fuels. These fixed sources are easier to change over time, and fossil fuels in coal are becoming more expendable. The UK actually stopped burning coal in March. They were trying to phase it out, and it turned out when their demand dropped a little bit and became started fluctuating in ways they didn't understand, they shut off their coal-fired power plants that were left. And I don't think they brought them back online either, which is interesting. If I've got a few minutes, I actually want to finish up with talking about how we model weather and climate and how uncertainty works in weather and climate modeling, and a little bit about how that applies to virus modeling, believe it or not. So as most of you probably know, climate modeling and global modeling of the atmosphere is essentially an accounting exercise constrained by physical laws. You take a giant spreadsheet that has entries for things like water, carbon, heat, wind, salt, kind of like you're tracking budgets of dollars and cents, which is what the example spreadsheet there is. It's actually a financial budget. You account for all the processes in every grid box where you have this spreadsheet, like the water in a cloud, and you solve the equations for these processes at every point. So you get a new budget, and you move things between boxes as appropriate. You advance this then in time and space, and you repeat it at every point on the planet. So you're carrying around a whole bunch of spreadsheets. And the art, of course, is figuring out what those processes are that move all this stuff around and change it, right? And the common problems are many of these processes are hard to describe at the right scale. We have imperfect representations. So, for example, if this is what a cloud looks like in reality, in a climate model, we only get 1 or 2 values to describe a cloud. So it looks more something like that. And we can usually only describe it with 1 or 2 values. And we also have to then fit processes that are variable or uncertain to our limited information. And we have to fit it from existing data, so-called empirical representations or parameterizations. Well, how do you model viruses? Well, a lot of the processes and concepts are actually very similar. This is a neat little model called the RT Live model. RT for R is reproduction rate over RT for reproduction rate over time. There's a website that has this. It has it by state. So this is yesterday's run for reproduction rate for California. So that's good news for all y'all in the Golden State. The reproduction rate is below 1. Reproduction rate is the number of people infected for every case of the virus, or it's sometimes called the transmission rate if you look at it in a detailed location sense. This is a critical metric for the spread of viruses. If R is greater than 1 and each person spreads it to more than one person, you get exponential growth. It's like having an exponent and the exponent is larger than 1, you will get exponential growth. If R is less than 1, then the number of cases decays over time. So you want R less than 1. The way this is estimated is it's estimated from lagged testing data. The nice part about this model is there's actually, you can go to GitHub and you can actually get the Jupyter notebooks that produce this, and you can actually look at and play with the model yourself. And so what this is it's not that dissimilar from other accounting exercises that I just described. You basically take in data. In this case, you take in positive tests. And what you do is you convolve, essentially what you're doing is you have the number of people positive today is the number of people positive at today minus 1 day or previous time times the reproduction rate. And of course, it's not that simple because this would be a single value if you knew every case, but we don't. We have an imperfect representation of the system. So we have this imperfect testing curve with the number of positive tests. And of course, each person tests positive at a given date. They're infectious for a certain amount of time before that. That's sort of a generation time. And there's a delay before they get tested. So they can give it to people over time, and they can give it to people over time at different rates, and there's a certain delay time. Those things you have to convolve into the model, and when you do that, you can then integrate over the days that they're infected, and you can actually try to represent this as a lagged curve. And from this hypothesized reconstructed green curve, you can then run this equation and get a reproduction rate over time. That's essentially how most of these models work. I'll skip that for now. But now I want to talk about, which is a different type of modeling for viruses, which is more element-based, but I'm going to skip that in the interest of time. So let's talk a little bit about uncertainty. So with climate, we want to know how bad will climate change be? What's the global average surface temperature in 2050? With weather, we want to know what's the weather tomorrow? What's the weather next week? Is there going to be, are fires going to continue because we have dangerous fire weather, or is there more moisture coming in? And with a pandemic, it's how many infections are we going to have in the U.S. next week or in our location? How many ICU beds are we going to need in the next month? Well, those of us who study climate and weather, and particularly those of us who do modeling, we know something about predictions and we know something about uncertainty and how to characterize it. So the interesting thing about weather and climate is their sources of uncertainties are different, even though the models themselves are actually very similar. You model the weather and climate in the same way. Weather, it's really the short time horizon you're interested in. So if this is January minimum temperature in Madison, Wisconsin, the weather is this all-time record low, which happened to be January 30th, 1951. The climate is this overall distribution, right? What I really want to know for the weather is, am I going to be here? Am I going to be at the tails of this distribution? What's the weather tomorrow going to be? And a lot of the uncertainty for the weather tomorrow has to do with the weather today. That tells you a lot about the weather tomorrow. So a lot of it is about the initial condition. In climate prediction, you're trying to predict this whole distribution on the order of decades to centuries. Part of the uncertainty is we don't know what society is going to look like and how much CO2 is going to be in the atmosphere in 50 years. We really don't care what the weather is on any given day, and the climate in 50 years does not depend on the weather today. So the way this works is that the total uncertainty is a function of the time scale and the lead time. So if this is total uncertainty, what happens is we have high uncertainty begin with at a detailed level. That decays over time as we go to larger and larger spatial scales where we're trying to estimate the uncertainty, and then it increases again. And this becomes, because initially if we're trying to predict the next few days, the biggest uncertainty in the near time scale is what's today's weather. So the current state of the atmosphere, the initial conditions, that's what really dictates the next day, the next week, the next month, even it affects the next year at the larger scales, at the global scale. There is a constant in there, which is the model or the structural uncertainty. These are the things like representing the cloud processes, for example, where we have to do that in empirical ways. And then the other thing that grows over time that people don't appreciate much about climate change is the scenario uncertainty. If I want to predict the climate in 50 or 100 years, what I really need to know is how much CO2 is in the atmosphere. And that's not actually a geophysical problem, right? Because that's the forcing, that's the total emissions, that's a human choice. And that scenario uncertainty grows over time. So when you worry about uncertainty, when you worry about weather, you worry about this part of the curve, and you worry about climate, you worry about that part of the curve. Again, the initial condition uncertainty is what is the weather today, or if you're thinking about a virus, it's how many people are infected right now. And both those are somewhat uncertain, as I'll show. We need to know for the model uncertainty how to represent clouds or how to represent virus transmission. And for scenario uncertainty, we need to know what are the emissions of CO2, or, for example, what social distancing measures are going to occur. Are you going to allow bars to be open, things like that. Getting data to constrain these things is critical. With weather and climate, we know the small scale, like the physics of clouds, and we know the large scale, global temperature. We have a hard time describing an individual clouds at the scale of 500 yards or 500 meters or so. For viruses, we also know the small scale. We know the physics of drops. We know infections of bodies. We know disease outcomes. And we also know the large scale. We know death rates. We know hospitalizations. We have snapshots for virus testing. But we have to put those things together to the scale of individuals mixing in an environment that we don't actually understand. So for weather forecasting, what's our initial conditions? Well, this is the problem of weather forecasting. We have errors in the current state that propagate forward. The way that you often solve this is you run multiple ensembles from initial perturbations, and you can understand where you could possibly end up from some slight deviations of where you are now, and that gives you not just one deterministic forecast of your best guess, but if you start in different places, you can get a range of all possible forecasts to give you the forecast uncertainty. Sometimes these ensembles cluster very tightly around a deterministic point. Sometimes they get very spread out. That tells you about your uncertainty in a forecast. The initial conditions come from data, so more data gives you better forecast. This is just an example from June of all the data being ingested at ECMWF. This is their data coverage, and it shows tens of thousands of data points from ships, automated met stations, there's some aircraft in here, and there's buoys, there's all kinds of things. You'll notice most of the data is clustered over land where it's easy to take observations. You can also make ensemble forecasts for viruses. This is an ensemble flu forecast, which is similar to the infection rate model that I showed you, but it's integrated in that it's run at different points, and then there's communication above those points. But you can start it in different ways and get different actual future forecasts of the scaled ILI is influenza-like illnesses. It's the number of cases of flu. This is done for Salt Lake City a couple of years ago. And this is another sort of model that's being applied to viruses right now. Initial conditions for virus models, these are from the UK, for example. This is they're based on infections, the rate of transmission and movement, and you predict how many people will get sick. Again, this is done for flu. So these are changes in transport use. So you can look at how many people are using their cars. You can look at vehicles. You can look at the rail system, and you can look at how many people are using public transportation. And then you can actually look at the number of confirmed cases. This is also input to getting those R values. And again, there's uncertainty in all these numbers, particularly in how well the case numbers reflect the actual infection rates in the community. And then there's structural uncertainty in the model. So I've just shown two equations here. The ones on the bottom from the virus model, that's from the RT Live model. I showed you that before. The one at the top comes out of the Morrison-Gettleman cloud microphysics scheme that's in CAM, and it's actually the budget equation for cloud water, Q, and its change over time in the modeling system, and these are all the source and sink terms. This is due to things like homogeneous freezing, there's sedimentation, there's melting, there's condensation, evaporation. autoconversion and accretion, which is the rain formation process. Each of these is an empirical or theoretical representation of a source and a sink term. For virus models, you have things you can observe, like the positive tests at different times, but they're uncertain, so you're estimating it. And then you have parameterizations. You have the total number of days infectious, you have the onset delay distribution, and a generation time or transmission distribution. So you have to basically deal with these same issues of model uncertainty in your forecast. You can actually perturb these things as well in ensembles, and people do that. They use parametric uncertainty to generate ensembles as well. And then finally, you have a scenario uncertainty. So what I showed you before is if you choose to emit 2 different amounts of CO2 and then run a whole lot of different climate models into the future, you get 2 different envelopes. The spread within the envelope of the same scenario is the model uncertainty. Those are what different models think could happen, convolving the model uncertainty with all the changes in parameterizations across 30 different climate models. But these don't overlap. And that's because the scenario uncertainty dominates as you get to the end of the century. So this one presumes a low amount of CO2 in the atmosphere. This one presumes a high amount of CO2 in the atmosphere. And then this is what happens with different scenarios, for example, with social distancing policies put into one of these virus models. Starting in the end of March, you can actually get very large or very small case numbers depending on what the social control measures are. Those are not part of the physical models I showed you. Those affect things like the transmission rate, or in the case of a climate model, that's the input to the radiative forcing calculation, is how are you forcing the system. All right, so just to finish up, COVID-19 and climate forecast. Essentially what we're describing for scenarios for the virus and for the planet is how much of each of these things is acceptable to allow. For viruses, biology is constant, drops, viability, comorbidities. In climate, the cloud and aerosol physics is also constant. Public health provides a macro picture. We get things like testing rates, and you can think of this in the climate context as like building an energy budget model, the climate system, where you're measuring the radiative fluxes and you know what they are at any given point and in the past. And again, these scenarios are critical. How much carbon dioxide do we emit? What is the radiative forcing? And for viruses, what policies affect the transition rate, right? And what can that do to the reproductive number? So what this does is it casts that in terms of the scenario uncertainty. You could actually project this forward by given different scenario uncertainties or different levels of people, people mixing or what you allow to open up as far as allowing virus transmission. Or you can look at that in a policy context for climate change. How much CO2 can we emit to get a given temperature? It's almost like saying how late can the bars stay open to avoid filling up our hospitals. But there's a lot of interesting social decisions based on that. So what you can see is that there's a lot of intersections here. I like the tagline I like to say is that climate change is just like COVID, but it's a lot slower and it's only going to affect our grandkids. Although you could argue with some of the impacts we're seeing with things like the fires, we're already seeing those impacts right now. And some of our environments now and our skies in the western United States are looking pretty apocalyptic in the same way that our lives are feeling pretty apocalyptic in a pandemic. So physics of clouds pollution, we understand there's some intersections there. We actually think that some of what we know about cloud physics can help. Virus spreads by talking and breathing. Masks help. And we do need more work at the intersection of aerosols and viruses. I think our community and the biological community and medical community doesn't talk very much at this level, and obviously we should be doing that a little bit more. Our world's upside down and people stop moving. Our air was temporarily cleaner, not this summer, but it was in the spring. But that has implications for climate change, of course. Climate change is only mildly affected by COVID. We see small reductions in CO2. Those are sort of offset by increases in radiation in the system from aerosols that offsets those greenhouse gas reductions. Stopping transport doesn't really solve the problem. Renewables are definitely benefiting, however, and it does provide pathways for showing us where we need to actually reduce our emissions. And then how do we predict the future? Where are the sources of uncertainty? Breaking things down into initial condition, model, and scenario uncertainty. Scenario uncertainty means understanding how viruses will transmit if we do certain things in our environment. Initial condition uncertainty for viruses is all about testing and tracing and understanding what the infection rates are. And the model uncertainty is the research into understanding how viruses transmit among people, getting back to these things like basic aerosol physics, which is also actually the critical uncertainty for climate models, believe it or not, is understanding the critical aspects of cloud physics. So hope I've given you a little overview and flavor of some of these interesting intersections, and there's some interesting things that you can take away from that today. And I think I'll stop there. So thanks for your time.
Thank you, Andrew, for a great talk, and we are all clapping, so you can't hear. It's a virtual clap. I know we're right at midday. For anyone who wants to ask questions and can stay longer, I'm presuming you can stay a little bit longer, Andrew, to take questions, right?
Yeah.
The idea is I think we might have you raise your hand, your virtual hand, and we'll scan down and then pick up the questions with those who raise their hand. So, folks, the floor is now yours for questions.
So we do have a question from Nathan. Do you want to just unmute yourself?
Yeah, just unmute yourself.
Hello, can you hear me?
Yeah.
Yes.
Great, thanks. Hi, I'm a bit of an interloper here. I'm at CCCMA in Victoria, but the link was passed on to us, and I'm very grateful. I really enjoyed the talk. Just have a question about the aviation modeling, which you mentioned. I was very interested to see those results. I just wondered if you could tell us a bit more about the modeling that you've been doing, and you mentioned that you had seen response in the upper atmosphere in the model. Just wondered if you could tell us a bit more about that. Thanks.
Sure, Nathan. Contrail model, it's basically bolted on. We basically take aviation emissions and the water vapor from aircraft into a climate model, and we decide if it should go in as vapor or as solid ice particles. I have a number of papers on that. So we can do that with the changes in aviation emissions. We're using a scaled inventory based on these drops in that we've seen in total flight numbers. Basically, you see reductions in contrails that doesn't actually impact the surface as much as you think, because the radiative transfer, obviously, you have long wave effects that are occurring in the upper atmosphere, and so the changes in temperature actually are dominated locally, and then some of them propagate down to the surface. But that's still in its infancy, and I can talk to you later about it and answer some more questions or set you onto the papers.
Great, thank you.
Okay, other questions? Don't be bashful, folks. I'm just scanning, let's go up and down.
Just unmute yourself. So Evan has a question about the aerosol comparison between MODIS and a model. Do you want to?
Is that Evan?
That's Evan. Yeah. Do you want to ask that?
Unmute yourself, Evan.
I'm gonna find that picture.
Can you hear me?
Yeah.
Yes.
Okay, so could you go? There was a figure where you compared, I guess, model aerosols, because I didn't completely understand all the talk, but you compared model aerosols from the model due to the change. I guess it was due to the change in pollution production versus from MODIS versus what your model said. And there was okay, great. This is a figure. So I'm looking at the rightmost column, and you can think of this. I mean, I think of this as being kind of a green function response of the Earth to a blip in pollution production, and we can see how the model responds to that blip, and they don't look anything alike. Now you suggested that it wasn't that these differences weren't statistically significant, but
no.
it sure looked.
No, what I'm suggesting, if you look at the scale, if I put the simulated difference on the same scale as the difference, you would see nothing. So the simulated difference is, I know exactly the only change in that simulated difference is due to the perturbations as a result of emissions. The observed and expected is trying to compare 1 month of data to a climatology of data with some hypothesis of controlling for the meteorology. So you're basically comparing 1 month to trying to make up a month without the emission changes based on prior years. And you get something that has some difference patterns, but it kind of looks like noise. There's no real logic to why those patterns occur. And what I'm saying is that what we're seeing is smaller than anything that you could try to detect in the observations as being a difference. If that makes sense.
Well, yeah, you're saying the observations on, I mean, to me, this seems like a pretty big perturbation to the system, and yet the two don't look anything alike.
It's a pretty big perturbation of the system because the difference from the observations includes meteorological noise, and the meteorological noise is much larger than perturbation to the system because it occurs over a limited time.
Right.
Okay, fine.
Next question, I think, was Michael, right? Michael Werner?
Yeah, I think you may have just answered this question. Extremely interesting and insightful talk. Can you, from the observations over the next few months or the last few months, hope to get any assessment of the validity of the climate models, given the perturbation that's been imposed on them by the behavior changes from COVID?
Yeah, I think we're trying a number of different avenues to do that. Contrails are one avenue for that because they've had the largest perturbation and we maybe can see it. But because when you're thinking in terms of climate and you're looking at in terms of months, the signal to noise is very low because the noise is very high. You're looking at meteorological noise. So we don't have the control case for the actual atmosphere. We only have the case that exists right now. What we can do in the model is we can run the same meteorology with and without, with perturbations to emissions and look at the effects. So I think there are ways of picking it out. We have to be a little smarter about how we're using our models and observations. And this paper by Diamond and Wood is just a first attempt at that.
Thank you very much. Good luck.
Okay, so as we get to the next question, Andrew, is by Mark Richardson. Michael Diamond has added a chat comment with respect to this particular slide. So if anyone's interested, they might want to read that as Mark is asking his question.
Hey, can you hear me?
Yeah.
Yep.
Thanks for the really interesting talk. This question is more about from if I want to go look at the epidemiological models and I see the results, they're reported all the time. What things should I look out for in their design, or is there anything you've learned for how to quickly judge the reliability of the models? I'm thinking of the early on University of Washington projections, and as far as I could tell, they just fit a statistical function that had to go down once it was over the peak. So have you got any other little things we should look out for these models?
Yeah, I haven't. That's a good question. I haven't looked enough into what the uncertainties are in the different models and don't have enough of a feel for that. I can see where in the simpler ones they're built, like that RT Live model, but that's only trying to estimate one of the parameters in some of these more complex models that are coming up with total case numbers across large regions. So yeah, that's a great question, is how do you understand the uncertainty? And I don't know the answer to that. I only know how to I only think we can characterize it and break it down, and that's a way to understand it better.
I guess I was more asking, is there a way that if you look really briefly at how the model is structured, you can tell for sure that this one's no good?
Not to my knowledge, based on the model structure. I would say the same thing is true of a climate model. If I just looked at the structure of a climate model, I couldn't tell you whether it was good or not. You'd have to look at the properties of the model, like past history, or does it conserve energy and mass, or how does it really reproduce reality? So I don't know that a model structure necessarily invalidates it, because a lot of it's dependent on the data that goes into it and how it uses the data.
All right, thank you.
Okay, well, thank you. I think we'll call that at the end. I don't see any other questions. So we'll let Andrew go off and have his lunch. So
thanks again. Thanks very much for
Yeah, thank you, Andrew, and we'll see you this afternoon. I think you have a few.
Yes, I have a few meetings this afternoon, so there'll be more chance to answer questions this afternoon.
Yeah, that was excellent. It was fantastic, really enjoyable, and I think the audience enjoyed it. So,
all right. And Michael Diamond, I didn't see the chat, so better send me your question, please. I'll talk to you about it later.
It was basically a comment, I think.
Okay, I'll talk to Michael about it later.
Yeah, right. Okay.
All right.
Thanks, folks.
Thank you.
Thanks for your attendance.
Yeah.
Enjoyable. Thank you.